Okay. Well, welcome to session 1 here at JUMPSTART 2021. My name is Corey Applegate. Let me bring up the slides here. Today's presentation is going to be on Robot Builder. Robot Builder is a tool that the programmers can use to help build up the backbone of our robot, of our Java or C++ command-based robot system. I'd first just like to thank Medtronic for hosting us today, along with Delta Modtech and St. Cloud State in the next few sessions here. The dates have been shared. I hope you guys look after this event for sessions you want to join there as well. Again, my name is Corey Applegate. I have 23 years as an industrial controls technician. I've worked with a lot of Lego robotics. This is actually going on my 6th year. That's a slide wrong. Hobbies include 3D printing of some CAD, as well as other programming. Today I have with me helping present is Natalie Fisher. You want to say hi?
Hello.
And say a few things about yourself.
Okay. Well, I'm Natalie. I'm a senior at Albany High School. I'm a member of Team 4226. I'm reading the presentation, so I've been co-driver. I've helped with build. I do a lot with scouting. I was drive coach for Infinite Recharge before things got shut down. Hobbies outside of robotics. I play saxophone. I don't know. Good enough.
All right, and I'd like to thank behind the camera there, we have Carter Calhoun and Justin Fisher, alumni of 4226 and 3244 respectively. They're running the switchboards and monitoring the chat rooms, as long as another coach of the Gearheads, Tony Lavelle, newly joined the team last year. So thanks for the people in attendance helping to monitor chat rooms and help with questions relay on to me. So moving on, we only have a few slides here and we'll go right into the live demo. So what we'll cover is we'll quickly create the backbone of our robot code using the Robot Builder. We'll open it up, the code generated in VS Code, explore the different parts of the project, test the robot's I/O, tune and test a PID system, and we'll do all this before we even write a single line of code. Then we'll create some commands, link them to our joysticks, and create some methods in the subsystems that a Robot Builder can't do for us. And we'll add some user code to control the drivetrain as well. Next slide. The pros and cons of the command-based robot program is the pros, we can develop and debug systems individually. If you have multiple programmers, you can have one person programming a drivetrain, another one programming a manipulator, and we can easily be compartmentalized and move on with and join these programs together. It's very well organized code. When we start with the Robot Builder, it structures it very well for us. It easily splits the functions I kind of alluded to, and we can reuse commands. If we have a command that we use in manual over and over or autonomous, we can trade off those commands and reuse those between the different modes of our robot. The cons, it does look complicated because there are so many different files you have to create, but really this complication allows us to ultra focus on a problem or a subsystem. We do have to treat some hardware differently. We can't just monitor for an input. If it's true, then this. We have to look at setting memory bits in the background. We're not going to touch much on that today, but there's a lot of documentation on the first docs. And we do have to make sure that we create our objects in the correct order. If a method or a subsystem needs an object that hasn't been created yet, you'll throw some null pointer errors. Next slide. So what is a subsystem? A subsystem is the different parts of a robot. It might be a gripper, a drivetrain, a wrist. You divide up all those little parts of your robot and what it can do. And this subsystem houses all the hardware for that subsystem. Next slide is going to be commands. Commands require a subsystem and actually tell the subsystem, here's what I want you to do at this moment in time. So we could stow a wrist or move to a scoring position, as you can see, drive to a goal, set an elevator to a position. So in the 2019 or the 2020 Robot Builder is what we're using today. It still outputs as the old command-based model. In that model, we have a robot. That's kind of our main program. The OI, which has been depreciated with the new command-based model. In 2021's, this will change. That software is near completed. It wasn't quite ready for this presentation. Same with robot map, it's been depreciated. And both those areas have been now kind of combined into one with robot container. So how commands work? Well, we develop these commands, and these commands might look like, first thing we want a robot to do is on a push of a button, it drive to a goal, raise an elevator, set the wrist in position, score the tube. Each method has an execute and an is finish. So we execute the drive to goal. When we get to the goal, the is finish is called, and it moves on to the next step. But we can also, instead of being everything is sequential, we can parallelize a lot of things. So maybe we can drive to goal, and then once we get there, we can set the wrist position and the elevator at the same time. Once those two are completed, then score the tube. So we save on time. So how is Robot Builder gonna help us get there? Well, we're gonna use menus and graphical user interfaces to build our subsystems and assign hardware to these subsystems. It's going to do some error checking for us to make sure that we don't put objects in places where they don't belong. We have drop menus that populate with only the valid options at that moment in time. And it creates a lot of the associations and many useful code entries that we have on our devices or that we have plugged into our robot. And without a line of code written, we can test components connected to that robot and see if they're operating as we would expect. And finally, it'll create a wire map that we can send to our electrician saying, if you wire up this robot with to these ports, the code will address them appropriately. So that's done the end of our slides. We're going to kind of move on to our live demo. I usually ask about this time as, people are new to writing code, and this is the great year to actually learn these new tools and to change from those different disciplines as C++ to Java or the other. Are we good back there? Okay. So once we fire up a VS Code project here installed with the WPI installers, we can go up to 3 dots and we can start our tool. This tool is pre-installed with our installer. So we're going to launch Robot Builder. First thing you'll get is this menu here, and we can give your robot a name. Just call it JUMPSTART 2021. I think that might exist already. Yeah. And assign it your team number. What you'll get is this application here popped up here, and we'll explore it a little bit. Down the left side is our menu system where we have our subsystems we can use, the different controllers we'd use in the subsystems, a lot of different drive controllers, all the different sensors that are preloaded, along with sensors that third-party libraries install, and sensors and output devices that you can create for yourself if you want to make some hardware with some more advanced options that you always can into all your projects. You can develop those, and we'll look at those when we look at the Talon SRX a little bit. We have one of those for example. Further on down is all the actuators, the pneumatic devices, and also finally the commands. The next little section here is our project tree. That's where we're going to actually build out our robot, and the final to the right is all the different options when we do drag a part in there. So when we build a robot, every one of our robots every year on kickoff or even before, you could be starting this because one of the most common subsystems we have is a drivetrain. So the first thing we can do is there's 2 ways that we can drag a normal subsystem, drag and drop it into the subsystems, and we give this a name. This is where you want to stick to your naming conventions. We typically use a my in front of what we name, so it really differentiates and pops up in our IntelliSense code. So we call this our my drivetrain. And we could also right click and add a subsystem. In this case, we're gonna do a PID subsystem. We're gonna call this my wrist. And we'll see these on our demo robot in a little bit. You can see there's already some errors popping out. That's some of that error checking saying we have to correct this beforehand. But let's start out with the drivetrain and start bringing in some components. In our drivetrain, we can add a controller. These are the different controllers, and we're going to add a differential drive. So differential drive 1, and you can see it automatically named that for us, and we can leave that as is. And this differential drive requires a left motor and a right motor. While on our demo robot, we actually have 3 motors per side, and they're all being powered with the Talon SRXs. So we need to create some speed controller groups. So we're going to add a speed controller group, and the first one we're going to call right speed controller group. And as you're typing these names in there, you can put the spaces in there. You can write your camel casing, the different naming conventions in there. When we output the code, it will automatically concatenate the spaces out and lowercase letters where naming conventions and industry standards deem. So we have our right speed controller and left speed controller. On the right speed controller, we're going to add 3 Talon SRXs. So we're going to add some actuators. We're going to install the Talon SRX. You can see that I named it Talon SRX1. We'll leave that, and it's a CAN ID of 0. We can add another actuator, SRX, and it's automatically renaming it into number 2, and it already incremented the CAN ID 1, and a third controller, Talon SRX, number 3, and CAN ID. These are the CAN IDs that the Talons have been assigned when we went into the Phoenix tuner and assigned the CAN IDs. And what these are actually plugged into, and what we do as a team, is we assign our CAN ID equal to the PDP port that we use. That way, when we're doing monitoring of any code and any issues, if we're seeing some current spikes on PDP port 1, we know it's the Talon SRX CAN ID number 1, and we can trace that out. On the left speed controller, we're going to do a little something different though. We're going to add our enhanced Talon SRX, and you can see it named it Talon SRX Enhanced, and we have a lot more options there. The Talon SRXs, we want to restore factory defaults, make sure the brake mode's set, all this other code that you're going to typically use every time you use a Talon SRX, this is going to automatically dump that into our code for us. So we're going to add 3, just like we did on the other side. And you can see Natalie there changed the CAN ID as well, because it's just continuing from the 0, 1, 2. But on this side here, we have it on port PDP ports 12, or 12, 13, 14.
13, 14, 15.
13, 14, 15. You're ahead of me. Yep. So those are all configured, and with well, you renamed them. That's fine.
Well.
So those are all configured, and you can see there's some errors in our speed controller groups. If we click on the right speed controller group, you can see that this is where the motors are assigned. And it's assigned number 1 to both 1 and 2. So we're just going to go ahead, hit the drop downs, and you can see it's populated with those motors that are actually underneath it. And if we click the left, that error will clear. And we'll fix up the left speed controller. And finally, the differential drive, we can see that it's assigned the right to both sides, so we'll just assign the left one, and everything's happy there. Final thing we're going to add to our drivetrain today is an encoder. So we can right-click on the My Drivetrain subsystem, add a sensor, and we have a quadrature encoder. It's the Robotics through bore encoder. And that encoder, we're going to give it a name of encoder, and that encoder has 2,048 pulses per revolution. But we're going to make this more like a user variable. So we have an 8-inch wheel on this robot today. So if we do some really fast math, and I would recommend you do a little bit quicker, we take that 8-inch times pi, or we'll go 3. We'll think 24 inches is 1 revolution of this wheel. If we take that value, 24 divided by 2048, we'll get a number of 0.012. So that's going to be 0.012 inches per tick of the encoder. So when we program our autonomouses, we'll have a more accurate, we can say, go 24 inches, it'll go 24. If that's not quite far enough, we can adjust that using real life user units. And that finishes our drivetrain for the day, for this moment. We'll go to My Wrist. On My Wrist, you can see it needs an input and output. And if you have any questions, please put it in the chat room, and my chat advisors, my chat monitors will let me know. So an input, the first thing, let's satisfy that. Or we can add, you're gonna add a controller first? Let's add an actuator. Let's add the motor first. So let's add a speed controller. Sense actuator?
Yep.
Speed controller. Today, what we're using on our wrist is gonna be a Vicker SP. She's gonna rename that motor. The type is gonna be Vicker SP.
There it is.
And it is plugged into the PWM port 0. And we're gonna add a sensor. And this is what we have for a sensor on this wrist today. Our wrist demo is an analog potentiometer. We'll call this POT. It is also plugged into port 0, analog 0. And a little later on, we'll see that this potentiometer, when we go full rotation, is 320 degrees. So we're going to tell the robot that full range of arc is going to be user units of 320 degrees. And we're done there. And you can see that it automatically fixed my wrist, and it is now black and happy. The next area we're going to do is we're going to look at the operator interface. We're going to add a joystick. We're going to name this joystick my Xbox joystick. Or joystick Xbox. As long as we name it the same all the way through, we'll be okay. We're going to add some buttons to this joystick. Today we're going to use buttons A, B, and Y. A is button 1. We'll call that A. Add a button. We'll call it B. This is going to be on button 2. And Y. This will be button 4. If we look at below on this one here, you can see the when to run. There's a few options down there. When held, hit the drop box. When pressed, and when released. This is when we're going to assign a command to this button, and this is when we want the command to actually execute. Either when held, so only when it's being held and you let go, the command will cancel. When pressed, as soon as we press it, we want the command to execute. Or on release. Might be good for a gripper situation where you push it, the gripper opens, and you let go, it automatically closes. So one button's doing 2 functions. We're going to set, eventually we'll be setting these all to when pressed. And we'll come back and review that in a second. So we have an operator, we have a joystick, and now we're going to add a few commands that we're going to need for our robot. Again, back to that drivetrain. Every robot, we're going to be driving our robot with joysticks. So we're going to add our first command here. We're going to call that my drive with joysticks, or joystick. Each command does require a subsystem. So you tell the robot program, I am going to get this asset, in this case, the drivetrain, and I require this whenever this is happening. So if another command says, I need the drivetrain now, it can cancel a running command and take over. But since the joystick command is, we always want that running if the drivetrain isn't being used, we're going to go back up to the my drivetrain and now assign it the default command of my drive with joysticks. And that way, if nobody's using the drivetrain, the scheduler in the robot program can say, you know what, joysticks, you have control of it automatically. You don't have to call and say, I want to control. The next command we're going to add is another drivetrain. It's going to be called my drive distance. This command also requires the drivetrain. So anytime we call this command up, it's going to take control from the joysticks, do its thing, and when the is finished method is called, return it back to the joysticks. In here, we're going to add a couple parameters, some values that we want to pump in. So we're going to add a parameter, and the first parameter we're going to add is set point. It's going to be a type double. We're going to add another parameter, and the next parameter is going to be speed. How fast we want the robot to go, along with direction, so positive, negative. That's going to be a double. And then the final is a turn, in case we want to tell it to give it a little turn. That's also going to be double. So save and close that. And then we should set up a default that we can look at. So we're going to create a parameter presets. We can create multiple parameter presets in here. But the first one we're going to call just default. And the variables, so set point, we're going to set to 24, which will be 1 revolution of the wheel. Speed, we're going to put at 0.3 just to slow things down a little bit so we can see it turn. And 0, we're going to put for turn. Save and close. And we could add many more other presets here that we can call. And the final command that we're going to add today is the my wrist to set point. This is a special one with the set point command. It requires a PID type subsystem. So when after she names this, you'll see the requires only gives us our PID type subsystems in that list. Again, some of that error checking, only giving us what we can use at that valid moment in time. We'll create some set point presets in there. Yes, why is she?
All right, so we got a question here, and that question is, does the robot builder work with the Spark Max controller?
Yes, right now Spark Max does not have the add-on profiles built into their installer package. on our GitHub, I have created one. I just haven't tested it fully yet. So I'd love to collaborate with somebody with one of those, but we have created an add-on profile. So you can create your own objects in here. We've created our Limelight object. So we have a library for our Limelight as well as the Spark Maxes, but we are a Talon SRX team, not the Neos. So I haven't personally got touched it, but you can build that add-on profile. And this is the time, this is the year, since we're not competing necessarily, to build up those tools. So all your programmers have those libraries, they drag it into their project, and everything will be structured the same. Very good question. So I hope that answered the question, and let me know if I need more on that. Natalie's moved on here, and she's adding 3 set points that we're going to use to stow our wrist, to present our wrist, and to pick. And we kind of, this is always back to that Steamworks ideas. When we had the gear, we'd pick the gear off the ground, we'd stow it in our robot, and we'd usually tip it forward slightly. If you can imagine that back in there. Or maybe even the hatch panels from several years ago, saving clothes. Okay, and now we're gonna go correct our buttons. So button 1 on the A, that's the lower button there, and that's gonna be our pick. So where you signed it, my wrist to set point, and you can hit this drop box. And you see those presets that we added to the command now pop up in this drop box. This is gonna be our pick. Button B, we're gonna set to present because it's that middle button on the joystick. And as she's finishing those up there, after we save this project here, this isn't the end of Robot Builders. What you're going to find with your programmers is they're going to use Robot Builder maybe the first week to build out some test code, to build the main body of the robot code. But after a week or two
just
in,
making sure I get them right.
button Y is going to be the stow.
Okay,
Yep.
that's what I thought.
We can return back here and make changes to our robot program, our Robot Builder as well, and we're going to explore that here in a little bit. So let's save before we do anything else, because it's always good in case something horrifically crashes. We'll name the file. Hit save. And now we're ready to export our core of our robot code, either in Java, which we're going to look at today, or C++. And you can see the project successfully exported, and we can look at it. And also, we'll take a quick look here at the wiring table. Here's this report you can hand over to your electrical group, and your other programmers are going to be setting up the hardware, saying, plug these devices into these channels of the robot, assign these CAN IDs to these devices, and the code and the robot program will, the code and the hardware will match up. So now let's go over to the VS Code, take a look at there. We're going to open up that folder that was created for us. So open folder, and if we can, it's loaded in the default location of the username FRC projects, and you can see there JUMPSTART demo code. We'll select the folder. The first opening of the code, since we are using third-party libraries, it is going to error because we need to import those. So as this thing builds out right here, we're going to see an error at the bottom on the first boot. We're going to right-click on Build Gradle. Down a little further, fourth one from the bottom on the tree. From the bottom. Build Gradle. Oh. Build.Gradle.
Yep.
And there, the fail, and we can manage vendor libraries. This is where you're going to import your Spark Maxes or your Crossroad Electronics device. So install new libraries offline. And the installed hardware on this computer is the Phoenix CTRE Phoenix. We're going to install those libraries, hit OK. And yes, we would like to rebuild after bringing it in. And you're going to see our code now goes all yellow and everything is happy. So let's explore VS Code a little bit for those of you that haven't looked at the command-based model and see what has been created for us from Robot Builder. The first section we're going to look at is the commands. And we can open up the My Drive with joysticks. In here, you can see all these begin auto-generated code, end auto-generated code. These are the sections that Robot Builder owns. So anything that you see inside these sections, Robot Builder created for us. And if we write any code in that block, anytime we go back to Robot Builder, regenerate code, it will be erased. So if you're going to write any customized methods, you're going to want to make sure to stay outside of these areas. And if you want to force Robot Builder not to own these areas anymore, you want to take control, and anything Robot Builder it should ignore, you go ahead and delete this header and footer of these sections, and Robot Builder will no longer manage these sections for you. So inside a command, we see several different methods that were automatically created for us. The initialize. When we call this command, what do we want this robot to do before we actually start running a subsystem? Maybe reset an encoder, set some timers, set some variables. The execute every 20 milliseconds or every scan of the robot code. This will be scanned and you'll get your data, update some motor speeds. The is finished is where you'll compare. You'll check that encoder, see if it's done, not done. When this returns true, when we write some code in there, replacing that false, this command will finish. And finally, there's an end and an interrupted. This is where we want to clean up after ourselves. Maybe shut the motors off, because how bad would it be if a command was driving our robot forward and somebody interrupted, said, I'm taking over, but didn't update the speeds of the motors? That robot would keep on going and try to escape the field. We've seen videos of that before. And then interrupted is that just that somebody interrupted me, or the end. In the new command-based model, these two methods have been combined together because they essentially do the same thing. And we'll look at what we need to do here. The other command is the myRisk, the set point command. We gotta move along here. There's some code for us that created all the necessary code we need for a set point command. Same methods in there, but we won't have to touch any of this in here. Now let's go look at our subsystems that were created for us. The My Drive Drain subsystem. As we scroll down, you remember the first section, we created some Talon SRXs, and the second we did Talon enhanced Talon SRXs. You can see all these objects have been created for us, have been assigned the CAN devices, assigned to the speed controller groups. But in the second area, we're going to see our Talon SRX is enhanced, and all these configurable parameters that we want to set our Talon every time. Because in the middle of a match, or middle of a competition, if you replace a Talon, that has the old parameter in there. So you got to be good about reconfiguring a Talon every time in case when somebody puts it in there, that way you know the state of the Talon. Scrolling on down, sets up our differential drive, our encoder, and finally our default command is set up for us already, a periodic method if we need to write some code to do some smart dashboard updates. And at the end here is where we're going to create our methods. Quickly, we'll go look at the IO. This IO and the robot container have been replaced by, click on the IO Java. Again, this has been replaced by that robot container, or am I getting that right? In the new command-based subsystem. Here's where all of our buttons have been mapped, assigned to our joysticks, buttons, some smart dashboard buttons have been put on there for us. And finally, the robot, the main part of the program, robot.java underneath IO.
Yep.
Here we won't really need to touch this until you get into some more advanced stuff you might want to do, but our robot init, when the robot starts up, creating all of our links, what to do when the robot's disabled, what to do when the robot's in autonomous mode, and what to do when it's in Teliat mode, calling the schedulers. So right now we're gonna power it up. We explored the robot code, but we haven't written any code, but we are ready to download this into the robot. So now you're gonna go up to the top corner there and deploy the robot code. Is this camera zoomed in a little bit on the screen too, or mostly on the robot? The whole picture, good.
You see that, right?
A build filled.
That's not.
Try.
Yeah.
What was Oh, the robot wasn't hooked up yet, so it's probably still booting up. Try again. I just powered up. We couldn't find it. There we go. And it deployed successfully. We're going to open up our driver station and take a look. So we're going to use this method, this mode called test mode today in the beginning here. So we're going to go to our driver station, click test mode, and enable the robot. And this tab up on our shuffleboard, live window, has been created for us here. Let's go in new. This has some old garbage on there. Refresh that live window. There we go. So we can see the wrist and the drivetrain have been created for us. And here, if you move the ungrouped over, expand the drivetrain, we can try running our motors. So we can pick the left side of our drivetrain, move the slider up and down, and we can see that that side of our drivetrain does turn. So we're testing our motors. We're looking at the Talon SRXs. They're all flashing. They're all responding, as well as the right side here. Positive goes in one direction, negative goes in the other, and all the Talon SRXs are responding. And also, go back to the other side. Go positive. You can see our encoder is updating as well. If we went slow enough, we could monitor that 24 inches would be 1 revolution around that. We can also test our PID controller. We can see that our analog input is at 0 volts right now, and if I crank it all the way up to 320 degrees, it goes in a positive direction. Because when we do PID control, the input and the output have to be what we call in phase. So a positive input should be a positive command output. So if Natalie jogs that motor in a positive direction, go a little faster, you can see that this motor is counterclockwise, and the counterclockwise on our wrist is also a positive direction. So they are in phase. And if they weren't in phase, we'd have to go invert one of those. And I would suggest that we would invert them in a logical manner. We can zero those. Now that we can test it, we tested all of our inputs and everything's working as we would expect it, we're going to start tuning our PID subsystem. PID control is one of the scariest things for a new programmer in FIRST Robotics, because usually you have to write a lot of sample code, deploy it, test it, create some outputs so you can monitor what's happening in there, react to any changes, redeploy. But with this robot builder creating these tools for us, we can start to tune our PID controller right now. So we can enable the PID controller. You can see it's trying to jog in a negative, and there's some analog errors in here, but it's trying to close that 0. The further I get away from 0, the faster it's going to go. If she puts the set point to, say, 90, you can see it's going counterclockwise, as well as as I approach 90 degrees, it's hunting that. So I can confidently say that we are in phase and everything's working there. But what we want to know, here's disable the, yes, sir. This wheel here? I don't have a Sharpie on me, but I verified it, and we're gonna put the belt on and we'll see it actually in action here in a little bit. So when we set up our motion, yeah, I can mark it.
Close enough.
Some contrast here. When we set up our input device, we don't want to hit max to max. And then today, even though our output device, our arm says it can go all the way back here, we're going to say that this is a hard stop. This mechanism can never go beyond straight up and down, as well as that is our down hard stop. So we're going to have a 90-degree range of motion. But what we want to do, instead of saying 90 is our 0 and 180 is our down, we're going to create some user units, and we're going to offset this. So right now we can see when we're straight up, our input is roughly 1.2 volts. If we take the scale of 320, we take 1.2 times 320 divided by 5 is a full scale, we'll get a number somewhere in the neighborhood of 76 degrees. So our 0 point is actually an offset of 76 degrees from max on the input device. So we're going to go over to Robot Builder, and we're going to apply an offset to our potentiometer of negative 76, because the 0 is actually negative 76 behind where our actual 0 we want to be. We also are going to go into the MyWrist subsystem, and we're going to set some limits on our input. So down there you can see a box there that says limit input. You check that, And in the input, we're going to put 0 and 90 degrees. That way, any programmer ever sets it outside those bounds, it will latch it in and make sure it's in bounds. And also, we're going to slow things down a little bit. We're going to limit our output. We're going to go, what did we say yesterday? 0.3,
Oh.
negative. Well, negative 0.3 and positive 0.3, just to slow things down so we can see how this all works. We'll save. Re-hit the Java button. We won't get any prompts this time, but if we go into our VS Code, we'll see that these updates in our MyRISC subsystem, these numbers have updated. Our outputs limits, our input limits, as well as our potentiometer. So we're going to redeploy this. Now we'll go back into our driver station, re-enable in test mode. And we're going to enable our wrist. And you can see the set point currently is at 0 and it's locked in up and down. If she puts 90 in there, you can see it is trying to close and go to 90. And as I get closer, it's hunting for that. So I'm pretty happy right now that everything is working, and I am ready to mechanically attach my output device to my motor because I can see that it is trying to get there, and we're going to tune our eye. So if you can disable that for a moment. We'll change our dial to 0 there and re-enable. You can see it's hunting for that 90. If she puts 0 in there, it'll come up to 0, and it's going to hunt for this. So now we have to start to tune our PID controller. So right now we can change our peak value. Let's try 0.5. Still hunting. Let's try another factor of 10, 0.5. And we can see as we're going here, we're tuning our PID, and we're happy with that. We can go in there and tune a lot closer, depending on the weights in there. But we're going to record that 0.5. We're going to go add that to our robot builder. And adjust, and we're going to change that 1 to 0.5.
0.05.
0.5, yes, you're right. Then we'll save, hit the Java button to push that to our VS Code, and we'll redeploy. And she's using the quick key of Shift F5. And now we're going to go into teleop mode with this and start to look at what we've created here and enable the robot. Let's go back to Smart Dashboard. You can see these buttons were created for us automatically. And we can look at the set point to stow, and we click that button, and it's up. Set point to present, it goes at 45. Set point to pick, it goes at 90. So without writing any code, our PID controller is acting on commands on a Smart Dashboard. But remember, we did map those to buttons. So pushes button A on the joystick. It's already down. So push button Y. It puts it stow. A for pick. And B for that present. So we haven't written any code yet, but yet we have buttons that are on our commands running our PID subsystem to where we want to go. But as she pushes the joysticks, nothing's happening there yet because this is where we have to start writing some code. So we can disable the robot. And let's go into the drivetrain subsystem. We're going to create 3 methods in our drivetrain subsystem at the bottom. This is where she gets to be a keyboard wizard.
Oh boy.
We're going to create the first method. It's going to be a public void
Down here.
my drive arcade. So the public is this method is exposed to all other parts of the robot. The void says that we're going to return null value. And the my drive arcade goes back to our naming convention. Whenever we use that IntelliSense, we type in my and it lists everything that. Open and close parentheses.
Nope. There we go.
Hit enter. Inside this method, we're going to control our drive, our differential drive 1. So she's going to type in differential drive. There it's popped up. You can enter dot arcade drive. We're gonna pick the first one here. And you see this requires two variables. We're gonna use the power of the IntelliSense to click on the light bulb and look at some choices. How do we fix this? We can create a local variable, a field, a parameter. A parameter is what we think we need. We want to input some stuff. So we'll create a parameter. It'll automatically create a parameter of double type speed, or speed with a double type. And the same thing with rotation. And that's it for this method here. We're going to create a second method here, a way to reset our encoder. So arrow down, get out of there, create a new arrow.
Wait a second.
There you go. Put it to a space, put another space there. We're going to create a method here called public void my encoder reset. And here we're going to call the encoder dot with lowercase e encoder dot reset. So now we have a way to reset our encoder from outside, and a third method to wrap this up. Our third method is going to be a way to get our encoder value. So we're going to do a public double this time. My get encoder distance. And here we're going to call the encoder dot get distance. Semicolon. Where's the syntax there? Oh, we have to add the return. So we need a return. So in front of encoder. Yeah. In front of encoder of that method there, put return. Yeah, we have to return. It's written on my notes. RE return, just type in return space, lowercase. There we go. Now we can hit save. Now that we have that done, we can go look at the drive with joysticks command that we created earlier.
There it is.
And in the nothing we have to do today in the joysticks needs to initialize. So we're going to go into execute and create some code inside the execute method. And what we want to do is we want to call robot.myDrivetrain .myDriveArcade. And you can see it requires those variables that we need. So we're going to, again, use the light bulb to create some local variables for both of them. And here, we're going to set those local variables to some joystick value. So we're going to go equals robot.oi. That needs to be capital R on the robot.
Got it. Guess I didn't have to delete all of that, but
Dot get. Or sorry, not get, dot my Xbox joystick. Yep. Dot get raw axis. Number 1 is going to be our speed input. And the same thing with the Z rotations, going to be robot OI, my Xbox joystick. Dot get raw axis 4.
Corey, just doing a quick time check. We'll go a little bit longer just to be able to make sure you can finish up since you started late, but
thank you.
Just awareness of the time.
Copy for time, Natalie, copy that robot drivetrain, my arcade drive speed, that third line in there, that method, and paste it into the end method. Copy and paste it in there. Set those two variables to 0. So when this is interrupted, we want to make sure we shut our motors off, as well as we're in the interrupted method, we're going to call the end. So let's go to the my drive with distance real quick. That way we have that done. Before we do the deploy, we'll skip ahead a little bit. My drive with distance. In the initialize method, type in the robot.myDrivetrain dot encoder reset. We want the encoder reset.
Yep, I got it.
In the execute, we want what you had there with the hit paste. You should be still in your paste. We're going to set the X speed to the M underscore speed, which has been up in the initialization. We'll put the rotation at the M underscore turn. The is finished method. This is where we're going to type in some code here, delete the false. And we're going to put in there some, we're going to go get that encoder and make sure it's greater than, so we're going to use the math function, capital M, math.abs, parentheses. And we're going to do robot.myDrivetrain.get my get encoder distance. And we're going to see if that's greater than, so arrow over once, space greater than, space underscore M set point. And in the end, we're going to make sure we turn our motors off. So we'll paste that, should be still in our clipboard, and put those to 0. And set that to 0. And finally, on the interrupt, call the end. Then we can deploy. Deploy that. We're going to go a little quicker here, skip around a little bit because I want to show you how some of these things are. This is the moment where we would test to make sure a forward is actually forward on a robot, reverse is reverse, left is right. And if we need to, we can go negate either the joystick input or the actual method, which in our case, this particular robot is the case we have to. So if we enable in test mode, or not test mode.
Corey, can you wrap up in 1 minute?
Yes. Drive it forward, drive the push up on the sticks. See the robot goes forward, backwards, left, right. And if you can see up here, there's a method up here called distance default. If she hits that button, you'll see these wheels turn 1 revolution. And from here, we can take these commands that we created and we can start stitching together our command groups. And you can go on the WPI. Let's go back to our slideshow. We don't have time to really copy and paste those into there. The last page or last 3 pages. That one right there. We should all be familiar with the FRC docs page. There's a lot of information on how to structure this code and a lot more sample code on how to build out your commands. But now that we have these commands, you can stitch these in order. And since I'm being cut short here, or not short, just cut off, we would love to demo that for you. So look for some videos. If you look at this, a search for on YouTube, FRC 2013 Robot Builder, there's a great 6-part series. It's back in NetBeans era, but all the data is still relevant today. Next page. You can, again, that's more the docs where to get more information. And as well, we answered some questions through here, as well as when this is done, this will all be put up to the JUMPSTART Robotics website, and there'll be some handouts that you can download. It will have all these links as well. So I thank you for joining us today on this week 1 of 3 for JUMPSTART 2021. And